All right, let's get on with it. We are going to write down the conditions for some of the conditions for a vector space to be a vector space, and then talk about subspaces. And in the next piece, we'll get on to our first awesome subspace, which is column space. Okay, very exciting. All right, so this gloss a little bit over over what vector space requirements are. This can get a little, this can get very fastidious, but we're going to be fairly practical about what we do. Okay, so the big story for us will be that vector spaces live inside vector spaces. And we're worried about these, and we'll call them subspaces. Okay? So there's going to be vector space requirements and then subspace requirements. All right. So I'm going to write down 3 properties for vector spaces here. I have, in fact, done that. And we'll use this notation. So let's just list these. So if x1 and x2 are in this vector space and you add them together, of course we have to worry about what addition means, but I want you to think just about vectors in the way we've done it. Then the sum of them is still in the vector space. If a vector is in the vector space, then any multiple is still in the vector space, and we're talking about scalars, so scalar, right, to scale. Any number, you can multiply by any number that's in the real numbers, right? So before there could be complex numbers, but that's what we're doing here. Bit of a funny one. If zeros, we need 0 to be in the vector space. That is clear from here, maybe. I mean, yes. Oh my gosh. Okay, there's a cat. And if recording my lecture. Oh. Yeah. So if 0 is in the vector space, and x plus 0 is still x, right? And so I haven't quite written that out. Let me write the other fabulous piece here. So these are pretty boring, right? I know you've thought generally that everything is interesting in linear algebra, and I don't want you to, be let down here, but it's just been a whirlwind of fascinating topics. But this little bit here is whatever. No, it's so vector space are a big deal, all right? But this may seem a little sleepy. So, and in fact, there's a series of, and I've written here, a series of increasingly boring conditions. And so we've got, you're allowed to, they're fine. It's a little crazy. So let me show you. You can go and look at this on Wikipedia, for example. So lots of different pieces. You have to test these things. And it's possible that a space could mess up on some of these. Good stuff, right? So there's associativity, commutativity, right? It doesn't matter which way you add it. There's a 0 vector is mentioned here. Okay. Right? Lots of things. But we're going to just focus on our good stuff here. All right, and we're really going to be thinking just about Rn, right? Our focus, and I know I mentioned donuts and things like that. Our focus will be Rn. All right? And in fact, that will include n equals 0, 1, 2. 0 is an interesting one. It's a little funny, but just 0. That's going to create some mild problems for us, but it's an important, very important subspace. Okay, so here is a super big deal is that vector spaces have subspaces inside them. Right, vector spaces, and these subspaces are vector spaces by themselves. So vector spaces have vector spaces inside them, depending on the subspace, unless it's, generally speaking, there's an infinite number, but vector spaces inside them, and we call these subspaces. I know, for some reason this will matter for ax equals b. We call these subspaces. All right, now if we know we have a vector space, then we only have to test 3 things. basically. So that's to check that something is a subspace. And if we went back to here, here we had this kind of story here with this isn't a subspace of R2, this is a subspace of R1. There are all these good properties of the vector space which we believe in that the subspace will have automatically if it obeys a few pieces, right? And another one was right here, not a subspace. This was not a subspace because they broke down on one of the rules. Okay, let me flash over here. So we have, yeah, okay. I think that's enough to say, going back to those things. So we'll have properties again. So we need 3 properties. So as I said, there are really many other properties here, but we need 3 properties for, and this is the right word, so for a subset, right? So a subset of V to be a subspace. Could be a bunch of points, right? And there are only very special subsets that are subspaces. So let's call them subspace property 1. Why is that a little weird? Okay, subspace property 1. The excitement builds. And then we'll march on very quickly from this, but this is a good thing to understand. I mean, essential thing to understand. Okay, so we're going to have these 3 things. They're going to look just like these other ones. And so we'll call, in fact, I should do this. I like doing this, so let me move that across. Subset, we'll call it S, right? Subset. So it's simply that if x1, you guessed it, and x2 are in S, then that's true for x1 plus x2. So we saw the subspaces that are on the axis, or the subset, which is all the points on the axis, fails to be a subspace for this reason. So that's true. If x is, so it's the same as these, then C times x is in that subspace. The one that failed was the one where we just took the points on the right half plane. Good. And this has to be true for all C element of the real numbers. And 0, the 0 vector has to be in there. Which, if we've got this second property, kind of follows, right? So, okay. Okay, good. All right, so let's get some examples in here. So of subspaces. And what's going on with this thing? So think about R2, right? R2. This guy. I don't know why it messes that time up. That's crazy. All right, so it just does. We'd just plug it in and it kind of blows its mind. So this is R2, subspaces of R2. All right, so any line, we've kind of got this idea, right? Any line through 0. So they're all very simple looking things. They can't, we can't have any bendy things, right? No banana shaped spaces. They have to be lines or planes, or they just have, they have to be Euclidean spaces within Euclidean spaces, right? So basically, R7 and R13, whatever it is. Any line through there. There are 2 others, right? So this is there are infinitely many of these. So that's one set. So let's give this a little star. What else is in there? All right, so it's the endpoints. It's a bit trivial. So R2 itself. That is a good subspace. and just 0 works too. So these are actually important. I'm going to highlight that perhaps. These are important. We'll get to a group. Oh yeah, lots of good things coming. Okay, yeah. So eventually we'll talk about, so if this is a subspace, then we'll talk about orthogonal subspaces, such that any point in the big space can be made up of a sum of a vector that's in one subspace plus a vector from the other subspace. But let's hide that for now. All right, so 0 works too. So 0 is good. One element. 0 plus 0 is in there. Any multiple of 0 is 0, and 0 is in there. I think I said that. All right. Groovy. Yeah, that's pretty good. Let's just say what happens for R3, right? So R3, the subspaces are. What are the subspaces for this character? Subspaces. Right, so we've kind of figured out these limits. So R3 itself is there. 0 by itself, cool. And then, when I say cool, I mean not very cool. But any line through, that's just a terrible thing. Any line through 0. By line, I mean obviously, right? And so these are that's the one-dimensional space, and then any plane that passes through 0 as well. Okay, cool. You might want to think of what's the orthogonal complement to a plane in 3D. What's the space that complements that nicely? All right, we'll get to that. That's going to take a little while. I think that's good. The next piece is going to be what this means for column space. And then we're going to go to null space, and then we'll go to row space, and then we'll go to left null space, and it's going to be awesome.